Hello, ladies. We are going to talk about potential difference or voltage today. Okay, and again, this is just part of our electricity unit, and we're going to introduce a little bit of a new term. So, potential difference. What potential difference is the difference of electrical potential between 2 points, i.e., it's actually the electrical force or the push that causes those electrons to go through a circuit, right? So you could think of it as a push of electrons that causes those electrons to go from one end of our circuit, from our negative terminal, to the positive terminal, okay? So to have a bigger push would be to have a bigger potential difference, and a smaller push would be have a smaller potential difference, okay? So when charges are separated from each other, so charges of opposite charge, then they have potential energy. They have the potential to flow back towards each other. Okay? When that energy is released, the electrons flow towards the positive charges. Right? If you have a negative and a positive, the negatives really badly want to go see the positives. When you release them, you're not holding them captive in their own separate quarters. The electrons are going to flow towards those positives. We could say potential difference or potential energy is also called voltage. And if you remember, we had volta in our previous set of notes when we were talking about the battery. And so voltage is kind of the name they came up with to pay homage to his work and what he did. Potential energy or voltage is then often measured in volts. And so kind of confusing in the sense that voltage is expressed by a capital V, but so is the unit for volts, also expressed in a capital V. So the nice thing is those units go with that particular variable, but they both have a capital V as their symbol. So we're talking about potential energy or voltage. We have an equation that's related to it. And again, just like our current equation, this will be provided to you, but you need to know what all of those symbols mean and the units that we use. So, potential difference, or we can say voltage, right? They mean the same thing. They're synonymous. Is equal to energy over my amount of charge, okay? My V stands for my voltage or my potential difference, whatever you want to call it, same. And it is measured in volts, which is represented by a capital V as well. My energy is actually measured in joules, and it's named after a guy whose last name was Joules. But that unit is represented by a capital J. And Q, our amount of charge, we've seen that Q before. That's the same Q as we had in our current formula. That is still measured in coulombs. Okay, so we have V for voltage measured in volts. We have E for energy measured in joules, and Q for amount of charge measured in coulombs with a C. So we're going to go through a couple of different examples. So if you have your calculators, this would be a good time to get them out so we make sure that we're on the right track. We have the formula V is equal to E over Q. And just like we did for current, we could also use the triangle to help us distinguish between the different formulas when eventually we isolate for E or we want to isolate for Q and it's not set up as such. So with this, we have our E in our numerator, our Q in our denominator. So our E will go on the top of the triangle, our Q will go on the bottom, and V will then fill that missing space. Okay, so again, how it worked out is if we cover V up, change that to freehand. If we cover V up with our finger, then we can see that we're left with E over Q. If we cover E up with our finger, we can see that E is going to be V times Q. And if we cover up Q with our finger, then we can see Q. Where am I going to put this? I don't know. Over here, just really small. Q is going to be, oh, that's too small. I'll put it here. Q is going to be equal to E over V. Okay, so we can find those rearranged formulas using our little bit of a triangle trick. We know that E goes on the top because it's the numerator, and then V and Q go on the bottom because those are the only places left for them. But the only equation you will be provided with would be this one here. Okay. So when we go through these examples, same 4 steps as we did when we were talking about current. So we're going to list all of our known variables and their values on the left-hand side, as well as what we're looking for. That's step 1. Step 2 is to be using the equation. Step 3 is we plug in our values. Step 4, we get a final answer with our proper units. So reading this example, we have 42 joules of chemical energy in a battery, and it displaces 7.0 coulombs in a circuit. What is the potential difference between the terminals of the battery? So the first number we have here is 42 joules. We know that energy is measured in joules, so that means our E value is 42 joules. Next, we have 7.0 coulombs. We know Q, our amount of charge, is measured in coulombs. So we get Q is equal to 7.0 coulombs. And we're trying to find the potential difference, aka the voltage. And so we don't know what that is, but we know our units for that is going to be V for volts. We are going to plug in or determine what equation we want to use. We want to use the equation in which V is isolated. So this one here, the OG one we're provided. So V is equal to E divided by Q. When we plug in those values, that gives us 42 all over 7. And when we plug that in, 42 divided by 7 should give us 6. Our units for voltage is volts, or our volts. So we should have our voltage is equal to 6 volts. Okay? And again, we went through those 4 steps. So 1, set up what we had. 2, tell me what equation I'm using. 3, plug those values in. 4, final answer with proper units. Okay? The next question says, what direction does that charge in the battery flow? So we're not actually doing an equation right now. It's just saying, where does the charge come from? What terminal does it start at, and what terminal does it end at? And we know that the thing that is flowing, the charge, those are all just electrons. So electrons are all piled up in the negative end of the battery. All my electrons here. And they want to flow to the positive end. So we flow from negative to positive. So the charge flows from the negative terminal to the positive terminal. All right. The next thing we have is another example. We have a couple more of those, just to make sure we're feeling pretty confident with the calculations here. So the next question is, if there are 56 joules of chemical energy in a battery with a voltage of 4.7 volts, what is the charge moving through the wire back to the battery? So here we have 56 joules. We know energy is measured in joules. So our E is going to be equal to our 56J, or 56 joules. We are also given that our voltage is 4.7 volts. So V is equal to 4.7 volts. And we are trying to find the charge moving. Charge is represented by Q, and our final units for Q should be C for coulombs. Oh, I changed colors here. And so we are looking for Q. So we're going to isolate that formula to find Q. We know that our voltage is equal to E over Q. All right, that's the formula we're provided, which means if we cover up Q here, we should get the formula Q is equal to E over V. Okay, that's the formula we're going to use. We could plug in our values, so E is 56, our V is 4.7, And when we plug that into our calculator, 56 divided by 4.7, that should give us 11.91. And we're just going to round to 2 decimal places here. And we need units. And the units for charge are coulombs. Okay? So the charge moving through the wire back to the battery is 11.91 coulombs of charge. Again, we have those 4 steps. What does the question tell us / ask us for? What is our equation we're using? Look how we could plug things in. Boom, a final answer with proper units. The last example we have here is what is the amount of chemical energy in a battery with a voltage of 6.8 volts, and if the charge it produces is 7.1 coulombs. So we have, what is the amount of chemical energy? So we're looking for our E. Our E is our unknown here, and our E is measured in joules. So we have some unknown amount of joules. We are given 6.8 volts, and we know volts is the potential difference or voltage. And we have 7.1 coulombs, which represents our amount of charge. Oops. Come on. There we go. 7.1 coulombs is our amount of charge, which is represented by Q. Okay. For our equation, again, looking back at our triangle trick here, we know V is E over Q. If we're trying to solve for E this time, we cover up E, so we're left with E is equal to V times Q. And we could plug those values in. So V is 6.8, Q is 7.1. So our E, 6.8 times 7.1, is going to give us 48.28. And we have our units, which are joules. Alrighty. So those are some examples of how we could solve for either of those 3 variables within our within using that same equation. So you are more than capable of doing that, again, following those 4 steps every single time. Continuing on, we also have something called a voltmeter. So a voltmeter is similar to an ammeter in the sense that it is still an instrument used to measure something within a circuit. But a voltmeter, believe it or not, will measure the potential difference or the voltage between 2 points in a circuit. An ammeter, remember if we think back to our current electricity notes, will measure the amount of amps or my current within a circuit. Voltmeter measures in volts, ammeter measures in amps. So a voltmeter is a device that measures the potential difference between 2 points in a circuit. Thus, it is measuring how big of an electrical force or how big of a push there is on those electrons to push them throughout that circuit. Okay. When we are working with a voltmeter, there's a couple of things that we have to do. And so these are going to be important when you come back and we eventually build circuits on our own. The negative end of the voltmeter must be connected to the part of the circuit nearest the negative end of the battery. Okay. Similarly, the positive end of the voltmeter must be connected to the part of the circuit nearest the positive terminal of the battery. Okay, so if we have a voltmeter and a battery in a circuit, so this is my plus side of my battery, this is my minus side. My voltmeter will also have a plus side and a minus side. So when we are connecting it in our circuit, our plus has to go to our plus, our minus has to go to our minus. Otherwise, you're not going to get an appropriate reading, and you could actually damage the device. So that is very crucial when we're setting it up, that the positive goes with the positive, the negative goes with the negative. Okay? Next, we're going to just talk about typical voltages, because you might have seen signs like, hey, danger, high voltage. If you go down Stafford, I think it's Stafford and Grant, there's that kind of electrical plant there on that transmission station. There, you might see signs on the fence that say, danger, high voltage. Okay? Certain voltages can be dangerous because they cause your current to increase. If you think of a voltage as being a push of electrons, the harder the push, the faster those electrons are going to travel. And if you have a faster current, because of your electrons moving at a faster rate, that going through potentially your body could cause you some serious harm. So it's not necessarily the voltage that's the danger, but the voltage is what causes the current to increase, and an increased current could cause you some serious damage. So if we're looking at typical voltages of your everyday household batteries, so AA, AAA, C, and D batteries, they typically have a voltage of about 1.5. So relatively low. If you touch a battery in both ends, you're not feeling any sort of shock, or if you do, it's very, very minor. Okay. Whereas if you have a household outlet, so where you plug your device into the wall, typically it's 110 volts to 120 volts, and that's typically what you would see in Canada and the States. But some countries around the world have higher electrical outlet voltages, so they might have something like 220 volts to 240 volts. That's why sometimes if you go traveling, you might need an electrical adapter, because if you put too many volts into your device when it's not used to it, or too few into your device when it's used to more, then it could damage your device as well. Okay, so that's why being shocked by an electrical outlet in your home will give you quite a big jolt compared to a battery, but not as big as something like a power station. Okay, so if you go to that power station, Grant and Stafford, a power station could have something like 110 kilovolts. And kilovolts is just times 1,000. So you have 110,000 volts to 1,200,000 volts, which is a huge amount compared to your household outlet. And a household outlet in itself can cause a decent amount of damage. You could get a pretty good shock from that. A power station is ridiculously dangerous. So that's why you see signs like danger, high voltage around power stations or electrical plants or things like that. Okay. A couple of things. Voltage and current, they are directly related, which makes sense. If I have a low voltage, that means I have a small push pushing the electrons around. If I have a small push, the electrons aren't moving that fast. They're only moving as fast as they're being pushed to go around. If I have a higher voltage, that's a stronger push on the electrons. And if I'm pushing them harder, they are traveling faster. Okay, so our current is our amount of charge over time. So pretty much the speed of our charge moving around our circuit, where our voltage is how big of a push we have to make those electrons speed up. So it's directly related. If nothing in the circuit is changed as the voltage is increased, then if the voltage is increased in the circuit, then the current is also increased. Similarly, if the voltage is decreased, then the current is going to be decreased. And that's assuming we keep everything the same. If we look at this image, it's great and awful all at once. This is an engineering's image from ages ago. But you notice that we have all of these positive charges, and it almost appears like these positive charges are moving, and that's so incredibly wrong, right? We know, get rid of those. We know that it's the negative charges that are moving. Okay, so I'm going to make this a little bigger. I'm going to just get rid of all those positive charges, because we know that that's not necessarily true. I'm going to get rid of this arrow too. We know it's the negatives that move. They travel from the negative terminal of the battery to the positive terminal of the battery. And I'm going to get rid of these guys too. But I wanted to show you this image so you could see that when you see things on the internet, yeah, they have their value, right? Engineers thought of this way before we figured out that the electron was negative, which is, like, they did a lot of valid science, but just because they got one thing wrong doesn't invalidate everything they said. They just switched up two facts. Here, it doesn't quite make sense when we're talking about electricity. So what we're going to do is, instead of positives, we're going to throw negatives all around this circuit here. Because that's how they travel, and they travel from the negative to the positive. Okay. And because the one at the bottom here, or actually before we do that, so they travel from negative to positive. Negative to positive, okay? The one at the bottom has a higher voltage, which means it's going to have a higher current, so the electrons are going to move faster, and so I'm going to show that by saying it looks like there's going to be more. It's not necessarily that there's more, it's just that they're traveling faster. And you can see that with the higher voltage, our light bulb is shining more brightly, right? Because the higher current and the higher voltage combined causes that to shine more bright, right? So if you plugged in a light bulb with 1 battery or 6 batteries, then you are going to have a different amount of voltage, right? They could all add up. One typical battery is 1.5 volts, so having like 6 of them, you're now increasing your voltage. You will get your light bulb to shine much more brightly than just having the 1 because of the increased voltage, which then implies the increased current. Okay. Similarly, if you are looking at that, it's like what we said before, the voltage is not necessarily the part that is dangerous. It is, in fact, the current that will kill you. However, the current, if it pulses through your body, that's only due to the high voltage. You can't necessarily have a high current without a high voltage. So they go hand in hand. So when you see danger, high voltage, that usually leads to a high current, which could cause some serious damage to your body. Depending on what's in the circuit, so if we add resistors to our circuit, resistors are just things that will slow down that current. We could still have a high voltage and a smaller current, which means that if the voltage itself is really, really high, we could still survive things with high voltages. So people survive when they're being hit by lightning, not always, but a good chance of the time, because they either were touching some sort of resistor, so it slowed down the current even though the voltage was really high. So typically speaking, if you're asking me what is dangerous, is it current or is it voltage? I would say it is current that is the most dangerous. But current is only dangerous when we have a high voltage because they go hand in hand. Okay? That is it for the notes for today, but what I really, really want you to do is there's this absolutely hilarious and interesting video about stun guns that is on this link here. So if you could follow that link, again, you can't click it in the video, but you could go to the slides that are posted on Teams, open up the document, and then go ahead and click on the link. It is worth your watch. You will definitely enjoy it. You will have no regrets, and maybe you'll learn something too. But otherwise, for homework, there is that voltage worksheet that you should be working on. The answer keys is, in fact, already posted on Teams, as well as a worksheet that follows, which is the current/voltage worksheet. So it takes the 2 equations that we've learned so far and puts them all into one worksheet. Okay? Otherwise, that is it for me. Have an absolutely wonderful day and enjoy the video. Bye.